So I'd like to introduce a thought experiment in this segment. Let's assume that we're trying to get an idea of some number. Let's say that we go to a third world country and there, there isn't a lot of information, and we want to know something random like the height of the male individuals in that population. Well, let's say that there's 300,000 males in the population. It would be quite difficult to measure the height of every single male to find the average height. So we collect a sample and we supposedly grab a random sample. There's going to be some distribution around what is truly the mean. And that original distribution, as you can see kind of in this picture, is going to be quite dispersed. If I increase my sample size, so maybe I go from sampling 2 to 8 to 20 to 100 individuals, well, my ability to predict the true population mean or the true average height of the males in that population becomes more accurate to a point where if I increase that to where n equaled the population size, so I measured all 300,000 males, I would know, not with any degree of uncertainty, but with perfect precision, what the population mean is. Well, that's the relationship here between sample size and sampling distribution. So intuitively, the more information you have, the better or more representative a mean is of the population. You have more faith in that mean. You tend to believe that the sample mean is closer to or equal to the population mean. So the standard error, as we discussed before, is equal to the standard deviation of the sample or the population. We're going to assume that they are equal, divided by the square root of n. So as n increases, the standard error decreases. This is an inverse relationship here. And so we can see that in this figure. As n goes from 4 to 16 to 64, then the standard deviation here would be the square root of 64. The standard error would be the square root of 16, and the standard error in this case would be the square root of the standard deviation by the square root of 4. So let's look at an example. Let's say due to problems in the filling process, beer bottles are not always filled to capacity. A certain brewery advises that the bottles contain, on average, 12 ounces of beer. So you can kind of think of that as the average of the population. We want to check that, so we grab a random sample of 100 bottles off the product line, and they yield a sample mean of 11.9 ounces with a standard deviation of 0.4 ounces. Well, that doesn't sound like much. It doesn't sound like we're too far off the 12 ounces that they expected. But the question that we have to ask is, how likely is it that the mean of 100 bottles will be 11.9 ounces or less when we expected the mean to be 12 ounces? So we can once again use the central limit theorem to assume a normal distribution. And when we calculate the standard deviation, we find that the standard error is equal to the standard deviation of 0.4 divided by the square root of n, which is 100. So we have a standard error of 0.04. So the z-score in this case would be 11.9 minus our expectation of 12 divided by 0.04, which is our standard error. So that would be 0.1, or negative 0.1 in this case, divided by the square root of, not square root, 0.04. So we have that calculation here, and that calculation gives us a standard error, or a z-score of 2.5, a negative 2.5. If we look at our normal distribution with a z-score of a negative 2.5, we find the probability of getting 11.9 ounces or less would be less than 1%. There's a less than 1% chance of that happening. Because that occurrence is so rare, well, we've got to assume that the population mean is something other than 12 ounces, is something less than 12 ounces. So the probability of observing a sample mean filled to 11.9 ounces or less is only 0.0062 or 0.62%. Assuming, that's the big assumption there, assuming the brewery's claim is actually true. Now, what would happen if we only sampled one bottle and we found that it was filled to 11.9 ounces? What is the probability of getting one bottle at 11.9 ounces or less? Well, we can see the difference here is that the standard the standard deviation that we use is 0.4 instead of 0.04, which is the standard error. And so we find that the z-score is only negative 0.25, not 2.5. On a standard normal distribution, that would mean that about 40% would be, even if we assumed that the mean was 12, about 40% would be 11.9 ounces or less. Well, that doesn't sound like it's too unlikely. In fact, it is fairly likely that a single bottle will have 11.9 ounces or less, even though we'd expect the population mean to be 12 ounces. So we would not expect that the average of the 100 bottles would be 11.9 ounces or less, but we are not surprised that only one bottle is 11.9 ounces when we expected 12.